Good morning, guys of grade 11. Today, inshallah, we're going to continue section 2 of chapter 12, was talking about the solubility process or the solution process. So, last time we really stopped at the point that not all the solid components that could be dissolved in any solvent. That means some solutes dissolve in certain solvents, and we actually classify this according to the structure of the solute and solvent. So we said that ionic compounds, they could easily dissolve in polar solvents like water could dissolve in most of the ionic compounds, because easily we could find here a strong kind of attraction force between the partially negative oxygen of the water and the partially positive hydrogen of the water with the different ions charge, or the cation and anion of ionic compound, which make them just separate and start completely to distributed within the water particles. So that's here how it's happened. While the non-polar compounds, okay, or we said that like the carbon tetra, okay, chloride or the toluene and this substance, they cannot dissolve that easily in water, or they do not dissolve in water, because the kind of attraction force between the water molecules and these compounds not that strong, so they cannot separate them, okay, while they still hold it together in a crystals, because the strong force found between their molecules, so they could not separate. So like this, they will not dissolve that easily. So today we're going to continue. We're going to talk about what happens when a liquid solutes and solvents. That means liquid does any two liquids could dissolve each other, or they could any liquid can dissolve that. For example, when you mix oil with water, could you find that easily dissolve? Of course not. You're gonna find that even after you're shaking oil with water and just leave them for a minute, you're gonna find they are separated into two layers, in which the oil is gonna be above the water, and they have a kind of separating line between them. On the other hand, if you get some of alcohol, like ethanol, for example, okay, which you have a lot of in your homes now, okay, and you start to mix it with water, you're gonna find they are completely mixed, or they are the alcohol dissolved in water. So in that case, there are some solutes they could dissolve in water, and the others cannot dissolve. So what that the idea, or how that could happen, or why some solutes could, some liquid solutes could dissolve in liquids and others not. So simply we could be classifying this into two categories: immiscible, okay, and immiscible. So the immiscible, they are the liquids, okay, that cannot be soluble in another liquid, okay, while the miscible one, they are liquids that completely, or they are dissolved freely in different proportions between different ratios, okay, with, okay, another liquid. So depends on what here, guys. For example, here, as we said, when we add oil to the water, that is immiscible. Why? Because actually the attraction force between the water, between the oil particles, okay, is somehow they are strong enough, okay, or that's kind of the attraction force between the oil particles is more than the attraction force that will be found between water and the oil. So as you can see here, for example, in that picture, toluene and water, once they are mixed, they are separated into two layers, as you can see, and there is a separating line between them. So what happens here? Actually, the water toluene molecules, they are have a kind of force between the molecules, which make them highly attached to each other, and the water molecules also, they have this kind of hydrogen bonds between the water molecules, which make them attached to each other, while the intermolecular force between the water and the toluene is weak. So in that case, water cannot separate, or water cannot separate the toluene molecules. In that case, okay, the toluene will keep attracted to itself, and the water are the same. So they are gonna produce two similar, okay, or two different layers. We call this, okay, immiscible substance. While in the other hand, which we get, okay, alcohol like ethanol, for example, and we add ethanol to the water, it's immiscible. We could easily find that the alcohol completely distributed and dissolved in the water. So the idea here that the repulsion force between, of the kind of this kind like alcohol and benzene, for example, the kind of the attraction force between their molecules, okay, and does not that strong, or that it somehow equal the force that will arise between the water and the alcohol. So in that case, the alcohol could somehow separate from each other and start to hide between the water molecules, and in that case start to dissolve. In another hand, there is another reason that the OH group in the ethanol, this hydroxide group OH, it's somehow partial or polar, that means have partial positive and partial negative, which causes a rise of hydrogen bond between water and alcohol compounds. So somehow that allows some of water of alcohol compounds to separate, or just to move away from each other and hide between the water spaces, or water molecule spaces. So in that case, okay, that's called dissolving of substances. So here there is a very important part here, guys. We said that gasoline in a solution composed mainly of nonpolar hydrocarbons, and it is also excellent solvent for fats. So like this, we could find gasoline. Okay, it could help in solving fats, oils, and okay, the major intermolecular forces acting between the nonpolar molecules are weak. Okay, that's which is London forces. Okay, so what do you call it? The London forces. While ethanol has intermediate medium polarity, that means it's not that strong polar like water. Okay, and at the same time, it's not weak like the carbon tetrachloride. So in that case, which make okay that water is good for dissolving the ionic compounds, while ethanol is good to dissolving okay the nonpolar compounds. So like this, we could find that each solvent could be suitable for dissolving certain solids. Okay, so here like this, we could find that the difference. Okay, or what actually the forces that is applied once we start to dissolve a liquid solid in a solid. Then we passed another part here, which is the effect of pressure on solubility. What is the effect of pressure? So simply we could recognize that the effect of pressure is not that strong, or we cannot slight change in the or slight effect of pressure on liquid and solid, because as we know that the distances or the spaces between the solid particles or the liquid particles is not that big, so the pressure will not have that effect. But as we know, in case of gases, because the particles of gases are far away from each other, there is a lot of intermolecular spaces between the particles of the gas. So the pressure could have some or noticeable, or that we say that a visible effect on gases. So in that case here, we could find that once we, in normal case, if we have a liquid and there is a gas in contact with the surface of this liquid, so some of these gas is able to penetrate or goes inside the liquid and start to dissolve, while some other particles of gas, they could escape and return again into the form of the gas out. That's well, okay, after a while that we are gonna reach a case of equilibrium in which the gas plus solvent equals solution. That means some of the gas will dissolve in that liquid and produce solution, and the sum of the gases particles which found in solution, they will break down, or they will just escape and turn again into the gaseous state. So in normal conditions, each gas has a certain limit or has a certain percentage of solubility, that means to dissolve in a certain rate or a certain ratio to the solvent, okay, and this ratio will never changes, okay, in normal situations. But once we increase the pressure, that means that we apply kind of pressure on that gas. In this case, we force the gas to move more inside the solvent. In that case, we increase the rate of solubility. So after a while, we're gonna reach this case of equilibrium, in which the case some of the gas liquid will also return back or the sorry, but because in the case of the pressure, if we keep that pressure, okay, so we are gonna find that the gas will be trapped inside the solvent, and that's here we will cause an increase in the rate of the solubility. That's lead to a Henry's law. So Henry's law, he said that the solubility of a gas in a liquid is directly proportional to the partial pressure of that gas on the surface of the liquid. What does it mean? That means the more the pressure you apply on the gas, the more solubility the gas will, or the more solubility of gas in that liquid. That means the gas will dissolve more under high pressure. To clarify the idea, let's take an application here in our daily life. That's here the bottle of Pepsi or the fizzy water. While the bottle is uncapped or still not opened, you cannot find any gas bubbles on the surface, okay? But once you start to remove the cap and start to pour it, you find a lot of gas. That's a lot of carbon dioxide come out. So what happens here? In that case, guys, actually, okay, while there during the bottling the Pepsi or whatever the fizzy water, it's already under high pressure. This pressure allows carbon dioxide to be completely soluble inside the liquid. It's trapped inside. But once you remove, okay, the cap, you unleash this pressure, or you just decrease this pressure, which allow a lot of gas particles to escape to try to get out, okay, away from the solvent, which cause all these bubbles to be produced, okay. So that's why when you keep it okay open for a long time, or after opening, it starts to lose its okay. This is because most of the carbon dioxide actually escaped out, okay. So here like this, okay, we said that for this effervescences, okay, that means this kind of rapid escape of gases, okay, because they were under pressure, but once the pressure is released, they could escape easily here, guys. So let's see here another factor that could affect the temperature. Okay, so what the effect of the temperature and solubility? Actually, we're gonna find that increasing the temperature decrease the gas solubility. Why? Because actually, as we increase the temperature, we know that the particles they are gonna get more energy, so their average kinetic energy will increase. So that will allow the particles of solute, okay, that means the gas has more energy to move, so it has more energy to escape from the attraction with the solvent. So in that case, the solubility of the gas will decrease. But in the other hand, we're going to find that temperature has a different effect on case of solid and liquid. So in case of solid and liquids, as the particles get more energy, okay, so they allow the particle of solvent to have more spaces, which allow solids and liquids to go through it or to break inside and just too high. So that means that increasing temperature increase solubility of solids and liquids, but decrease solubility of gases. But actually, we find that the increasing temperature, okay, and it increases the solubility of the solids, but actually that's harder to be understood. They have different each substance, each solid substance has different behavior as temperature change. So as we could observe here in that chart, it represents here different solid substances that dissolve in water at different temperatures. All of them we find that by increasing temperature, the rate of dissolving it increases, but we could find that rate, okay, is completely different. We don't have a fixed rate, okay, of this increase in the dissolving. For example, you could find that potassium nitrate, while just slight change in temperature could lead to a huge change in solubility or increasing solubility in a higher rate. While, for example, if you could observe to the lithium sulfate, actually increasing temperature that allows substance to dissolve or increase the rate of dissolving certain point, and then it will start to decrease. So here there is not a specific rule that explains the rate of increasing solubility of solids in liquids or by increasing temperature, but generally, or what we could predict from that graph, that by increasing the temperature, okay, the solubility of solids could increase. So to understand that, let's find here an example. So if we're gonna compare the effect of temperature on the solubility of sodium nitrate, okay, and the sodium chloride in ACl, so we're gonna find that 14 gram of potassium nitrate dissolve in 100 gram of water at 0 degrees Celsius. And this solubility increases up to from 14 to 150 gram, okay, once the temperature reach 80. So that means once we raise the temperature 80 degrees Celsius, it's allow, okay, that's about more than 10 times of the amount to be dissolved. But in the other hand, if we look to the sodium chloride in the same circumstances, sodium chloride just allow 2 grams, okay, to or increase the solubility just with 2 grams only. Okay, that means 2 grams of H2O. Okay, but once we decrease the temperature, okay, we just reach 17. Okay, that's mean once we raise from 0 to 80, only 2 grams more of sodium chloride they dissolve it. So that means it differ from one solid substance to another. And here, as we said, for example, in cesium sulfate, we could find here between 0 degrees Celsius to 6 degrees Celsius, the solubility of cesium sulfate decreases, it start to decrease. So there is not a specific rule, okay, or there is not a just kind of a specific behavior for the solubility of solids by increasing temperature. So let's pass to the last part in our lesson, which we call that enthalpies of solutions. What mean by enthalpies of solution? Enthalpies that represent the change of energy that could happen, okay, during solubility process. So actually, scientists observed that the solubility process or dissolving, okay, is associated with a change in energy. Why we have this kind of energy? Let's take a first example. For example, when you dissolve the potassium iodide Ki in water, you're gonna find that the tube or the beaker that you are dissolving in feels cold. That means the surface of the peripheral is cold, which means this kind of solubility absorbs energy. While once you dissolve the same amount, but from sodium hydroxide, you're gonna feel that the beaker or the tube, the containers feels hot, which means there is kind of energy is released. So here like this, that represent clearly a difference in energy. Okay. So why that's happened? So first of all, we're gonna find that so per process, okay, just gonna pass by 3 steps. First of all, once we have the solid and the solvent, the solute substances or the solid substance, its particles or its molecules actually are attracted by intermolecular force that hold them together. And the same happen in case of solvent. The particles of the solvent, they are attached to each other by solid-solid attraction, while here solvent attraction, here solid-solid attraction. There is a kind of force between the solid molecules, and also there is a kind of attraction force between the solvent molecules. So to be able to dissolve this solid in that solvent, first of all, we need to break down the kind of attraction between the solid. That means we need to over the solid-solid attraction force, and the same we need to get over the solvent-solvent force. Okay, so here like this, the solid start to separate. So to overcome these forces, we need amount of energy. So like this, the solid particles start to separate, which means energy needed to come or to get over the solid-solid attraction force. And here the solvents start to surround the solute and start to move, okay, it apart. So in that case, also we need energy to come over the solvent-solvent attraction force. So here that means in this two step, in the step two, which we already get out of, or sorry, step one and step two, in the step one and step two, we requires energy or we absorb energy. Why? To overcome the solid-solid attraction force and the solvent-solvent attraction force. So we add these together because both are absorption, okay? Then here in step three, once already the solvent particles start to attract it to the solvent, okay, there is a new kind of attraction force arise now. It's a kind of attraction force between the solvent and molecules. So that is a solid solvent attraction force. This is going to release energy. So if the amount of the energy which is released less than the amount of energy which is absorbed in step one and two, that means adding step one to two, then okay, we are gonna minus step three. If this is more than that, actually in this case, okay, that will be okay an endothermic, or that will be a reaction that absorbs energy. But if the amount of energy that is released, okay, in step three is more than the total amount of energy needed in step one of two, in that case it will be an exothermic reaction, or that's a reaction that releases energy. So here like this, we could find that and represent, or this table represent the enthalpies of solution. That means the amount of energy is. So actually, if we have this in negative charge, okay, in that case, it means they already releasing energy, while in positive charge, that means they absorb energy. So here, the enthalpy of solution could be defined as the net amount of energy absorbed as heat by a solution when a specific amount of solid dissolves in a solid. That means how much the amount of energy is absorbed, okay? So in that case, we're gonna add the energy needed in the step one and the step two, okay? And then we're gonna just look at or compare it to the energy of the step three. If the energy in step one and two more than the energy in step three, so that in that case it will be an endothermic solution that absorbs heat. If it's less, so it is an exothermic solution which is releases heat. So here, guys, that's our lesson. I hope it's okay. Please study very well from your textbook, and if you have any question, I'm waiting for your questions. Please answer the section review, and we are going to discuss next time. Thank you, guys, and goodbye.